Let's take a look at writing numbers in scientific notation. When we look at numbers in scientific notation, we're really looking at scientific numbers, like numbers that are used to measure things in science. For instance, like the distance from the Earth to the Sun is 93 million miles. All right, that's a very large number. Or a drop of water weighs 0.00011 pounds. All right, a very small number. So when we look at these numbers, there's lots of zeros in the number. All right, so to write them down repeatedly and to do some arithmetic with those numbers becomes very cumbersome. So what we like to do is to simplify a number. For instance, 93 million miles would simplify to 9.3 times 10 to the 7th. And 0.00011 would turn into 1.1 times 10 to the negative 4th. These are numbers that are written in scientific notation. And the thing about scientific notation, this form always looks like this. A times 10 to the n. All right, so we have a number here for A, and one thing about that number is that A has to be between 1 and 10. All right, so we want there to be just one digit and then the decimal point. And then when it comes to the power, n just has to be a positive or negative whole number. So n must be an integer. Okay. Then we'll have a number that's written in scientific notation. So how do we do that? Well, let's say we have a scientific number like 201 million and we want to write it in scientific notation. Well, we know that scientific notation has this form where there's some number times 10 to a power. And what we need to figure out is what's the number and what's the power. So there's going to be just a few steps to do that. Our first step is going to be to move the decimal. So what I mean by that is that every number has a decimal point in it. With whole numbers, that decimal point is at the very end. And we want to take that number and move it all the way to right here, right after the 2. That's going to be our first number. Remember, this number has to be between 1 and 10. So we move that decimal point to right after that first important digit. That gives us our A. Next, we have to figure out what the power is going to be. To do that, we have to count places. What I mean by that is we started off with the decimal point at the very end, and we moved it to right after the 2. We need to see how many places we moved it, so we could just go back and start counting. 1, 2, 3, 4, 5, 6, 7, 8. It took 8 steps to get from the very end of the number to that 2. That 8 is going to be our power. The last thing we need to check on is whether that power should be positive or negative. And how you figure that out is you think about the first number. Our first number was 201 million. That is a big number. Big numbers are going to mean positive powers. That's because when we have positive powers of 10, so something like 10 squared, that's going to mean 10 times 10, which is 100. If we had 10 to the 6th power, that's 10 times 10 times 10 times 10 times 10 times 10, which is 1,000,000. 1 million. All right? When we have something like 10 to the 8th, that's 10 to the 6th times 10 to the 2nd, which ends up being 100 million. And so anytime we have a positive power of 10, we're going to deal with a large whole number. So how about when we have a small number, a number that's smaller than 1, and we want to write that in scientific notation? The steps to do that are still the same. We know we want to write it in scientific notation, so we'll have some number times 10 to some power. To find those numbers, we're going to take the decimal point, which now, with the small number, the decimal point is already explicitly in the number. And we want to move that so that the decimal point is right after the first non-zero digit. All right, so right after that 5. Then what we're left with at 5.1, that's going to be our A. Now we have to recognize what the power is. To find the power, we get that by counting places. Our decimal point started right here, and we need to move it to right after the 5. How many places is that? 1, 2, 3, 4, 5 places. That's going to be our power. The only thing left to do is to check whether that power should be positive or negative. And we said with big numbers, the power is positive. Well, 0.000051 is very, very small. Small numbers are going to have powers that are negative. Okay, so this will be -5. The reason for that goes back to what negative powers do. If we had 10 squared, remember that was 100. But if we have 10 to the negative second power, the negative power puts that 100 in the denominator of a fraction. So it's really 1 over 100, which is 0.01. Okay. If we had 10 to the negative fifth, like in this problem, 10 to the negative fifth is going to be 1 over 10 to the fifth, which is 1 over 1, 2, 3, 4, 5, right, which would be, as a decimal, 0.00001. All right, something that's very, very small. So, overall, big numbers have positive powers of 10. Small numbers have negative powers of 10. So let's try a couple more. If we're going to write 0.000000725 in scientific notation, we need some number times 10 to a power. To get that first number, we move the decimal point from where it is to right after the first non-zero digit. So 7.25. Then to find our power, we're going to get that by counting places. So go back to where the decimal point started and count how far it took to get where it ended. And that would be 1, 2, 3, 4, 5, 6. And we'll have a power of 6. Last thing, should that 6 be positive or negative? Well, think about the number we started with. Our number was 0 point, right? It's a small number. Small numbers have negative powers. So here is our number in scientific notation. One more, 68,700,000,000. All right? If we want to write this in scientific notation, some number times 10 to some power. The number is going to come by moving the decimal point from the very end to right after the first non-zero digit. So 6.87. To get our power, we count places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to have a power of 10. And because 68 billion is a large number, that power should be positive. And here is our number in scientific notation. So what about going the other way? What if I have a number that's written in scientific notation and we want to write it in standard form? Really, when we take these two important numbers that are in scientific notation, the number that's out in front and the power of 10, it all has to do with moving a decimal place. Because technically, scientific notation means taking 6.32 and multiplying it by 10 to the ninth, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Multiplying 6.32 times 1 billion, which ends up being 6,320,000,000. Now there is a quicker way to do that. If we take a look at where we started and where we finished, notice that we started with the 6.32, and in our final answer we have that 632. Notice that this is not a decimal point but a comma. Right? There's not necessarily going to be a comma where the decimal point was. How we know where the commas go has to do with the power. The decimal point started right after the 6. So in our final answer, if we take a look, our decimal point started right here. And we needed to move it 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. Down to the end here. And everything between that 632 and where we put that decimal point ended up being all zeros. So if we're going to take something like 3.7 times 10 to the 5th and write it in standard form, how I do it is I start with that 3.7, except I don't write 3.7. I write 3.7. Then I think about the decimal point. The decimal point was right here in between the 3 and the 7. We need to move it 5 places. And because 5 is positive, that means that the answer we end up with should be a large number, telling me that my decimal point should move in this direction. Because as we see the number change from 3.7 to 37, that number is getting larger. So we're going to let this number get larger by moving the decimal point to the right 5 places. So there's 1 place, 2, 3, 4, 5. This is where my decimal point is going to end. We need to fill in that space from after the 7 all the way down to that decimal point with zeros. So then it's customary to put a comma every 3 digits in a large number. So to clean this up, this would be 370,000. With 9.03 times 10 to the negative 5th, now we recognize that that power is going to be negative, which means our answer should be small. We should have 0 point something as an answer. So our form's going to be the same. That we're going to start with that 903. The thing is, I'm going to put that 903 over here because we're going to have to start off with a 0 point something. Okay? Then I start counting places. Okay? Initially, my decimal point is right after the 9, and I need to move it 5 places, and this time we're going to make it move to the left in order to create a number that's small. Right? So we just start counting places. 1, 2, 3, 4, 5. That's where our decimal point should end, and we should fill in this gap with zeros. So we need a 0 here, 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 and here. If we want to clean it up just a little bit, it'll be 0 point. And if you like grouping things in groups of 3, how we do that with decimal numbers is to have your group with 3 zeros, create a tiny space, and then we would go with 0, 9, 0, little tiny space, and then 3. That just kind of visually breaks up that decimal number. Let's try one more. 4 times 10 to the negative 7. All right. Ask yourself this first. Should this number end up being a large number or a small number? And it should be a small number because that power is negative. So I'm going to start with my 4 over here. Currently the decimal point is after the 4, and we need to move it to the left 7 places. So 1, 2, 3, 4, 5, 6, 7. This is where my decimal point's got to go. So we'll end up with 0 point and fill in the rest of these with zeros. So I need a 0 right here, 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 and then the 4. So this will be 0 point 0, 0, 0, 0, 0, 0, 4.